What's up? I want to show you a trick that viruses use to hide execution from users. The virus code, highlighted in red, is first injected into a program denoted by the green box on the left. Just to recap what we've talked about, when an infected program is run, the virus will execute first before the host program runs. The virus code will try to spread by replicating and inserting itself into other programs, for example, by searching for targets in the current directory. Obviously, we don't want to slow down the infected program because it's going to catch some attention if a program that usually finishes in a blink but now takes a couple seconds. Performing large directory tree walk is very time consuming. A naive solution is to perform long-running work inside a forked process. For those who are not familiar, fork is the way you spawn child processes that can execute code in parallel to the original parent process. This way, the infected program can run alongside the virus and users shouldn't notice any slowdown. But there are two problems with fork. If the virus code inside the child process runs too quickly and terminates before the original infected program's process dies, we'll have a zombie process that is very noticeable. Let me demonstrate what that means. I have prepared an example program that forks a child. In this branch, if the returned PID is 0, we are the newly created child process. Let's terminate right away to simulate the case that the virus code has finished very quickly. The other branch will be executed if we are the parent process. Here we sleep for 10 seconds so we can actually see why forking is bad. And then it performs a blocking wait to clean up the dead child. This is the canonical way of cleaning up kernel resources taken up by the child. Let's compile and run it in the background. Using the PS program, we are able to see both the parent process and the dead child process, which is marked as defunct here. This is because the child has died and the parent has yet performed blocking wait to clean up the dead process. Imagine we run a virus in the child process and finishes sooner than the infected program. This can raise some eyebrows when someone looks at the output here. The second problem of this naive solution is when the virus code performs long-running work and the parent started to perform blocking wait. Let's modify the code here. We'll add a sleep in the child to simulate long-running work, and then remove the sleep in parent. Let's compile and run it. You can see that the parent is being blocked, waiting for the child to finish. Imagine every time someone runs an infected program, they will notice that the program somehow gets stuck during startup, and that's no good for virus survival. For the sake of demonstration, let's double check that it doesn't spawn any zombie processes. As you can see, we don't have any zombies here that are marked as defunct. The trick some viruses use to solve this problem is called double fork. As the name suggests, it involves forking twice in a row. Our framework has a handy library that works just out of box. Let's read through the source together. In the common folder, we have a double fork function that can perform arbitrary work in the form of a callable, like a lambda or std function. It first forks a child process, and then the child continues to fork a grandchild process. The long-running work is performed inside the grandchild. Even though the original parent process does a blocking wait here, because the child process exists so quickly, the user shouldn't notice anything. You might ask, what happens to the grandchild process if the child process is cleaned up already? It will automatically get transferred to the init process, which will be responsible for its cleanup. So the net effect is we're not blocking the parent process to a noticeable degree, while also not creating any zombie processes that can catch attention. This is pretty neat, and you will see in the future that this trick is used in all kinds of viruses I'll be talking about. So keep this in your stash. It might come in handy someday. That's it. I hope you liked the explanation here. If you want to see a more systematic introduction to virus engineering, please check out the links in the channel description. Have a good one. I will see you next time.